Hello everyone, welcome. My name is Rohan. Today we'll be talking about generative adversarial networks, also known as GANs, in 5 minutes, and this will be a paper-based explanation. All right, so let's get into it. So let's start in the abstract. So in the abstract, they describe two models: a generative model that captures the data distribution, and a discriminative model that estimates the probability that a sample came from training data. And so they liken it to a two-player game. So let's imagine that there's a police and an art forger. And so this art forger is trying to get their piece of artwork into the Louvre. All right, so the art forger is going to make a painting, and it's not going to be very good at first. So this is my best drawing of a painting. And so then he's going to send this to the Louvre. He's going to try to send this to the Louvre. But then the police is going to stop him. He's going to stop him. He's going to say, hey, let me check that. And how he's going to check that is he's going to look at the paintings that are already in the Louvre, such as the Mona Lisa. And he's going to compare these two. So he's going to say, is this similar to this? And then he's going to make a judgment as to whether the painting the art forger made could have belonged to a real painting in the Louvre. And so because this painting is pretty bad, the police officer is going to say, hey, this is a fake painting, and the art forger is not going to be successful. Now, let's say after a couple epochs of training, the art forger can make a much more beautiful painting. So let's make this painting more beautiful. Let's add some colors. Make these mountains brown. And then the art forger has learned, and he's made a more beautiful painting. And so then the art forger is going to go again and try to get his artwork in the Louvre. And then the police officer is going to stop him again, and he's going to say, hey, could this painting realistically be a painting in the Louvre? And then he's going to look, he's going to reference an image from the Louvre, and the Louvre here serves as an analogy to the data set. So he's going to look at another painting in the Louvre, and then he's going to compare it, and he's going to say, hey, could this painting that the art forger made possibly be similar to this painting? And this time, let's say the art forger gets through, the police officer is fooled. And so this painting gets to be in the Louvre. And then the police officer learns that, hey, he made a mistake. So then now the police officer is learning. And so now both the art forger and the police officer are learning. So when the police officer catches the art forger is learning to make a better painting. And when the police officer unsuccessfully catches the art forger, the police officer is learning to make a better judgment. And so both of these things, the art forger and the police officer learning together, makes this art forger really, really good. And so after a lot of epochs, the art forger can make this really beautiful painting. Let's add some gold frame to it. And he can make a Louvre-worthy painting. And at the end, the police officer has no way of differentiating between the art forger's painting and the Louvre painting. And so now the art forger has successfully trained, and he's now making Louvre-worthy paintings. So let's go back to the paper. And so they talk about, at the time the paper was published, 2014, the most successful discoveries have been discriminative. So let's say you're using the Oxford Pets data set, and a discriminative application would be like determining the species of an animal, whether it's a dog or a cat or a parrot. And then deep generative models haven't been as good, and because of the limitations of existing models. And so they propose the adversarial nets framework. And so the adversarial means these are competing agents, just as we described. And so here we'll go into a more technical explanation. So their idea is that there's going to be one model, a generator, and another model, a discriminator. And keeping up with, one last thing is going to be true distribution. And so keeping up with analogy, the generator is going to be the art forger. The discriminator is going to be the police officer. And then the true distribution is going to be the Louvre. And so what's going to happen is that if we have a true data distribution, let's say this is what it looks like. And so all data has a distribution of audio, images, text. And so let's just say this is what the distribution of paintings in the Louvre looks like. So the generator is going to make an approximation. And then a discriminator is going to learn to differentiate between the green line, what the generator's learned distribution is, and the true distribution of the data set. And so over time, the idea is that we have our true distribution again. The generator will perfectly approximate this true distribution. And so the generator basically cannot do anything. And you know this when the generator is making 50% true predictions, correct predictions. That means it's truly random, and the generator has approximated the true data distribution. Okay, yeah, so that was that figure. And then next, the authors are basically just talking about a mathematical justification for their ideas. And then before we get to experiments, I'll draw the structure of the GAN, the overall structure of the GAN really quickly. So in this case, we're doing images. So we can say something, we'll start with something like a noise vector. And it has to be random, and we'll come back to that later. And it will make the image. Then, so this is the generator. What the discriminator will do is it'll take this image and so this one will be from data set, and this one will be from generator. Oops. And then what's going to happen is these will both input to a discriminator prediction. And so this is the discriminator. And so then the gradients from this will back propagate into the discriminator and the generator. So hopefully that's clear. And so now let's take a look at their experiments. So they tested it on the MNIST data set. So this is a really famous data set of handwritten digits. They also tested it on the Toronto face data set and CIFAR 10. And so you can see these are examples of quote-unquote fake images generated by the generator. And so we can notice two things. First of all is that these are extremely convincing. If you've looked at the MNIST data set, you can see that that 0 right here looks really like a digit you would find in the data set. And even a face like this looks incredibly realistic. This begs the question, though, how do we know that the model isn't memorizing the data? And so the authors address this by showing for each image in this column, they're going to show the closest image from the data set. And you can see that in each column there are differences. In MNIST, it's a little less apparent. But if you go to the Toronto face data set, you can see that these images are different. And so it is not just memorizing the training data set. It is generating new images. Okay. And so one last question is, how come this isn't deterministic, right? Because if we go back, if there's one distribution for the data set, let's say paintings in the Louvre, there's one distribution that describes this data set, or the Toronto face data set, or MNIST data set, there's a distribution. If the model learns an approximation of it, how come every image it generates isn't the same? In other words, how can it generate things as different as a 7 and a 0, right? Because you would think it would either generate the same thing or some sort of mean of everything. And the answer is this noise vector and the randomness. And so because that noise vector is random, it makes this whole system non-deterministic. And so each time it's going to make a new prediction that's not memorized from the training data set, and it's going to be unlike previous predictions. And so yeah, I highlighted this first extension that they pointed out, which is conditional generative models. And so what conditioning is it's essentially adding other information such as a prompt or something to essentially make it to guide the generation. So let's say, you only wanted to make digits like a 7 or a 2. Conditioning could do something like that. And so, yeah, that was GANs in 5 minutes, a paper-based explanation. Thank you very much, and see you in the next one.